We are discussing the second part of electrostatics today from physics. The second part, in the sense, mainly we are concentrating on capacitors. We all in fact know Q is equal to CV, the basic equation, where C is called electric capacity and of course Q is said to be the charge, V is called potential, C is equal to Q by V, the general formula. But of course we all know Q of a spherical object, we people used to write that one as 4 pi epsilon naught into R. R is nothing other than the radius of the body. The radius of the body we used to represent that one by R. So what we should understand in this case is, every body can have capacity, but a body has got charge also by any chance. Then the body, in addition to capacity, will have even potential also. That means what you can understand, C is proportional to R. This is the basic equation or relation. Therefrom you can write C1 by C2 is equal to R1 by R2. For example, two bodies or two spheres having radii in the ratio 1:2 are taken up. What is the ratio of their capacities? Suppose if they ask, then it is straight away 1:2 only, because C1 by C2 is equal to R1 by R2. Likewise, when you take this particular equation, what is electric capacity of earth, they may ask you. That of course we can say 4 pi epsilon naught, which is 1 by 9 into 10 power 9 into the value of R, which is radius of earth, 6400 kilometer. That in the sense we can say 64 into 10 power 5 meter we can write. Now of course you can cut this 10 power 5 over here, 10 power minus 4 times. So it is 64 by 9 into 10 power minus 4 you will be getting. Right, 7.11 into 10 power minus 4 farad, that is going to be the capacity of earth as such. That means when you know the radius, it is enough to calculate what is its capacity in general. So this is one area we have to cover up before taking up the applications part of it. Come to the second one, a parallel plate condenser. When we consider, what exactly is its use also we all know. It can store very high amount of charge at a very low potential. And what is its formula for capacity? Epsilon naught K A by D. Out of that one, this K is called a dielectric constant or a relative permittivity, and A is the area of the plate, and D being the separation distance between the plates as such. So if you take this one is said to be C in the medium, when medium is there in between, C air, suppose if I take epsilon naught A by D we write. So taking these two, K, which is called dielectric constant of the medium in between the plates, that can now be written as C medium divided by C air. This is one formula we have to remember. So what you can understand from this equation, please? C medium is always greater than C air. This is possible only in the case of capacitors. When you talk about electric field strength, when you talk about electric potential, when you just take up the force between the charges in electrostatics, in all those cases E medium will be less than E air, F medium is less than F air, V medium is less than V air, excepting capacity, all other values with the dielectric constant it will reduce. That is the point we have to remember. Come to the next one over here. By considering the parallel plate condenser, what is the resultant capacity when we connect parallel plate capacitors in series? One, of course we know, in series, what are the things which are going to be constants and what are variables? We can all understand charge remains constant in series circuit, whereas C and V, these two are going to be variables. Now the question next is, how do they vary? V is inversely proportional to C. So how to write that concept here? V1 is to V2 is to V3 is 1 by C1 is to 1 by C2 is to 1 by C3. In other words, you can write C2 C3 is to C1 C3 is to C1 C2. The same manner, 1 by effective capacity of the combination is equal to 1 by C1 plus 1 by C2 plus 1 by C3. This is the formula by means of which whenever parallel plate capacitors are connected in series, one can estimate the effective capacity, that is of the combination. Come to the next one, please. When we connect these capacitors in parallel, then what happens? Whenever we are connecting the capacitors in parallel, there we find that the potential difference across the plates of each and every condenser or capacitor, that remains constant. When capacitors potential difference is constant, C and Q, these two are now variables as such. How do they vary now is the question. Q is proportional to C. In other words, Q1 is to, Q2 is to, Q3 and so on will now be written C1 is to, C2 is to, C3 and so on. That means more is the capacity, more will be the charge on the plates of the condenser or capacitor. That is the point. Now in addition to that, effective capacity in parallel combination we can directly get by adding all the individual capacitors in that particular circuit. This is actually the formula by means of which effective capacity can be calculated when capacitors are connected in parallel as such. That is one area. Come to the next one in the same manner. What is the influence of dielectric on the capacity of a condenser? If at all we consider a parallel plate capacitor this way, if I just place in between these two a dielectric medium of constant K having a thickness say T, and the distance of separation between the plates of the condenser is D, and A is going to be the area of each and every plate. In fact, if both the plates are having the same area, absolutely no problem. If one area is larger than the other, then the common area is to be taken up. Which will be the common area there? The smaller area itself is to be taken as the common area of both the plates as such. That's one concept. Now what will be the capacity of this particular system? It can now be written as epsilon naught A by D minus T plus T by K. This is the formula by means of which we can estimate the capacity of a parallel plate condenser when a dielectric of constant K having a thickness T is introduced between the plates as such. Now here there are three separate subconditions. Suppose if the plate whatever we are using over there is a metal, that means for a metal plate used as a dielectric, K is going to be infinity for every metal. Therefore, T by K now becomes 0. Thereby, C becomes epsilon naught A by D minus T. That is the formula when a metal plate is taken as the dielectric in between the plates as such of thickness T. That is the point. Come to the second one, please. If at all the thickness is equal to the distance of separation between the plates, this is the distance of separation, this is T. If T is equal to D means what? The total space between these two plates is completely covered with a dielectric of constant K. That is the meaning of that. Then what can we write here? Then C will now be epsilon naught K A by D. Directly you will be getting the formula. What for means T is D means T and D they get cancelled. In place of T I can write D there. D by K, K going up to the numerator, it becomes epsilon naught K A by D. This is the formula by means of which under this particular condition one can calculate the capacity of a parallel plate capacitor. Now come to two more points over here, please. Look at the next one. Sometimes that fellow used to say there is a parallel plate capacitor this way. Half of that area of the plate is covered with a dielectric of constant K1. And remaining half of the area is covered with a dielectric of constant K2. Distance of separation between these two plates is given as D. What will be the effective capacity of this particular combination, they may ask us. In such a case, we have to consider that till this extent this is one condenser, the lower part is another condenser, both are now in parallel to each other. That is the concept one should understand from the figure. So what will be the capacity of the upper condenser now? Epsilon naught K1 A by 2 by D. Likewise, what is the capacity of the lower part of this one? Epsilon naught K2 into A by 2 by D. You can understand now both are connected in parallel. Then what will be the effective capacity of the system now? Simply C1 plus C2. By simply adding these two, you can get the effective capacity. Exactly like that, they may ask you the other way sometimes. The distance of separation is given as D. Half of this particular distance of separation is filled with a dielectric of constant K1. The remaining half of the distance, it is filled with a dielectric of constant K2. That means the total distance is made into two equal halves here. But means what? Areas are equal. Here areas are made half, distances are equal. So that is the point. Then you should understand this is one condenser, this is another condenser. Both are now in series. That is the point you have to understand. So what will be C1 in this particular case now? C1 is epsilon naught K1 A by D by 2. Because the distance is made half here. Likewise, C2 is equal to epsilon naught K2 A by D by 2. Now, what will be the effective capacity of the system? C1 C2 by C1 plus C2. Because all of you know 1 by C is 1 by C1 plus 1 by C2. If you take LCM and reciprocate that one, you will be left with C1 C2 by C1 plus C2 only. This is the formula by means of which effective capacity in this particular case can be calculated. Let us come to the last concept here. What exactly is going to be the value of energy stored in a condenser? Energy stored in a condenser, generally we used to call that one as electrostatic potential energy that's going to be stored in a capacitor or condenser. That formula is either half CV square or half QV or half Q square by C, whichever formula that of course is valid according to the data provided to us in the problem. That particular formula we can apply out of the three. Likewise, when two condensers or capacitors are connected there directly, what will now be the loss of energy of the system? They may ask you sometimes. You have a direct formula for that. Half of C1 C2 by C1 plus C2 into V1 minus V2 whole square. V1 is going to be the potential difference across the first condenser. V2 is going to be the potential difference across the second condenser. C1 is the capacity of the first condenser and C2 is of the second. So half of C1 C2 by C1 plus C2 into V1 minus V2 whole square. Like that we people can calculate loss of energy. Likewise, one more connecting concept for this one is what exactly is going to be the common potential when two different capacitors are connected, or when two different bodies having different charges, different potentials and different capacities are joined by means of a connecting wire like a conductor, then what would be the common potential? Common potential generally we write this way: total charge divided by total capacity. You know, in fact, V is equal to Q by C formula. Q1 plus Q2 by C1 plus C2. In other words, C1 V1 plus C2 V2 by C1 plus C2. This is the formula for common potential one can remember. So when we talk about capacitors in particular, these are the different formulae one should remember before taking up the applications on capacitors, please. And every time at EAMCET level, they are asking at least one question on capacitors. There were occasions in previous papers of EAMCET, Both the questions of this chapter electrostatics were asked directly on capacitors only. Remember that way, means capacitors is very important as far as this electrostatics chapter that is concerned. And the questions what we have taken for this particular chapter, they are the questions given in the past 12 years of EAMCET papers. So that way you will also be knowing what is the method they are following and what kind of questions they are asking based on capacitors as such. So let us start taking up the applications part of it, please. The very first question, a parallel plate capacitor has a capacity 8 into 10 power minus 6 farad. When air is present between the plates, the volume between the plates is then completely filled with a dielectric slab of dielectric constant 20. The capacitor is now connected to a battery of 30 volt by wires. The dielectric slab is then removed. Then the charge that passes now through the wire is how much? That is the concept. So very clearly, if you look at the entire problem, once he is talking about with the dielectric, the second time he is removing the dielectric, that means accepting air, nothing is there in between the plates as such. What is going to be the charge in both the cases we just want? Let us consider with the dielectric. With the dielectric, whatever he has given you, you can directly understand Q is equal to actually CV formula. But Kc into V I can write. That is the concept actually we should take. Actually Q is equal to CV. Now what is K given here? It is given 20 and C is given 8 into 10 power minus 6. So 20 into 8 into 10 power minus 6 into what is the potential difference across that one? It is 30. So this is actually the charge when there is a dielectric in between the plates of the condenser. And what that fellow did after that? He has removed the dielectric from the system. That means what will be the Q now? It is without dielectric. That is what actually he is giving indirectly. So without dielectric means if I take the charge as Q2, that now is going to be simply C into V because K is not there. Air has got K value 1. So you can directly understand C value is 8 into 10 to the power minus 6 into this value of 30. That is the second value. So what is this question actually? Charge that passes now through the wire is how much? That is nothing other than the difference of these two. Q1 minus Q2 is how much? Directly you can take 8 into 10 power minus 6 into 30. If you take common, 20 minus 1, that is going to be 19. So if you just subtract the values one from the other, whatever the value you get, that itself is going to be the charge. You will be getting exactly 45.6 into 10 power minus 3 coulomb. 45.6 into 10 power minus 3 coulomb. That means the option exactly is going to be the first one. Observe the wording carefully. With dielectric, without dielectric. He is asking you the charge that is passing through. So with dielectric, what is the charge that is passing through? That is there on the plates. And without dielectric, what is the charge on the plates? Calculate them separately. Take the difference. That itself is the excess charge flowing across the system. That is the point what we have to remember. That is question number 1. Look at the second problem, please. A fully charged capacitor has a capacitance C. It is discharged through a small coil of resistance wire embedded in a block of specific heat S and mass M under thermally isolated conditions. If the temperature of the block is raised by delta T, that is the variation in temperature, the potential difference V across the capacitor initially is how much? That is the concept. Wonderful question. He is just linking up this electrostatics with one of the chapters of heat and thermodynamics. You can understand what is the energy stored in a capacitor. Energy stored in a capacitor, in fact, we know very well, half CV square. He has given you the capacity value as C and potential difference across the system is given as V. So half CV square I can write, that is the total energy. What next he is giving you? it is now discharged through a small coil of some resistance. And of course, he gave mass given, specific heat given, delta T the rise in temperature given. Then what will be the quantity of heat energy that of course is generated across? Ms into delta T. Ms delta T, that is the formula. This is the second one. So according to our calculation, energy should be conserved. That in the sense what? Half CV square must now be equal to Ms into delta T. S being specific heat capacity, M being mass, and delta T is the variation in temperature. It has been raised through that particular value he has mentioned in the problem. Delta T of course he has mentioned with a capital letter. Let us write even this one also with a capital letter, nothing wrong. Now what will be V square? Is it not 2 ms into delta T divided by the value of C, please? But what is this question? What is the potential difference across the plates of the condenser is the question. So you can understand directly it as 2ms into delta T whole divided by C whole under root. Under root means you can all understand that is to the power half as such. So just to look at this option and compare with the options given over there. 2ms delta T by C whole power half. The second option is going to be the correct option for this question number 2. Right? Let us check the next number please. Two identical condensers, capital M and capital N, are connected in series with a battery. The space between the plates of M is completely filled with a dielectric medium of dielectric constant 8. And a copper plate of thickness d by 2 is introduced between the plates of N. D being the distance between the plates he has given. Then the potential differences across M and N are respectively in the ratio. That is the question. Now observe carefully what he is talking about first of all. He is just describing the question. There are two condensers which are now connected in series like this, connected across a cell this way as mentioned. Fine. This is M given, this is N given. This is completely filled with a dielectric of constant K. And here what he is talking about? A copper plate of certain thickness. What is that thickness given? D by 2 is introduced between the plates of N. So what you should understand here, you see, what is the capacity of the first capacitor M? Is it not epsilon naught K A by D, please? You can understand because identical condensers he is talking about. That means their areas of cross section of the plates are equal. Distance of separation is same. Everything same. But here there is a dielectric of constant K. Here there is a metal plate of thickness D by 2. That's what he is giving us. So look at the second one. What will be the capacity of the second capacitor, that is of N? What is Cn, the second one? Then we should write epsilon naught A by D minus T, because actually D minus T plus T by K we should write. But for a copper plate which is a metal plate, K becomes infinity, therefore T by infinity becomes 0. So you can directly write this one epsilon naught A by D minus D by 2, because thickness is given D by 2. Then is it not epsilon naught A by D by 2, please? So you can even write that one 2 times epsilon naught A by D as such. Fine. But what is the value of dielectric constant he has given in the problem? 8. So 8 epsilon naught A by D. This is the value of Cm and this is the value of Cn. Now you just write what is the ratio of their capacities first. Epsilon naught A by D here also we have. So that gets cancelled. 8 is to 2. 8 is to 2 means what officially? 4 is to 1. Fine. Till that extent excellent. But he is not asking you the capacity ratio. He is asking you the ratio of potential differences. So I should now write what is Vm is to Vn. You can understand well, potential is inversely proportional to capacity when connected in series. I have already mentioned that point in the beginning today. then automatically you can write Vm is to Vn is equal to Cn is to Cm. What is Cn is to Cm? 1 is to 4. That must be the correct option for us. So check that option number 1 please. 1 is to 4. But suppose if he is asking us the ratio of capacities, then the answer would be the second one, 4 is to 1. But he is asking you the potential difference ratio, therefore automatically that becomes 1 is to 4 over here. That is question number 3. Look at the next one, that is problem number 4 please. Consider a parallel plate capacitor of capacity 10 microfarad filled with air. When the gap between the plates is filled with a dielectric of dielectric constant 4 such that half the area of the plates is filled with it. Half the area, remember that, half the distance, it's not given like that. Half the area of the plates is filled with it. The new capacity of the capacitor will be how much? That is the concept. Look at first, when air is taken up between the plates of the condenser, one should understand C1 is equal to epsilon naught A by D. That is actually the equation. But now what he is talking about, this is the condenser. Half of this area is now covered with a dielectric of constant K, which is given as 4. Now remaining half, what do you have here? You are having air here. So half of that area is covered with dielectric, means remaining half is left like that only. That means we are going to have air. I have already given you C1 if I take of this particular capacitor. This I take C1 this way. Now C1 is equal to how much? Epsilon naught K A by 2 by D. Likewise, what is C2? Epsilon naught A by 2 by D. Then what will be the effective capacity of this one please? C1 plus C2. What to write now? Epsilon naught A by 2D you take common. Epsilon naught A by 2D if I take common, K plus 1, that is now left over. So can't you just write the same thing this way? K plus 1 by 2 times epsilon naught A by D please. What is the given value of K here? It is given 4. So 4 plus 1, 5 by 2 into epsilon naught A by D. That is the concept. But you can all understand, according to the first equation, is not epsilon naught A by D is C1 please. So what to write now in this particular case? You can directly take the value in terms of microfarad. As such, what is the first value given? It is 10. So you can write this one 2.5 times C1. What is C1 given? 10 given. So automatically this becomes 25 microfarad. So what is 25 microfarad corresponding to? The first answer that is given as 25 microfarad for us for this problem number 4. So that is the correct option for it. Remember, half the area is only covered with a dielectric. That is the clue from this particular problem. Look at the next problem, that is problem number 5. Two capacitors of capacities 1 microfarad and 2 C microfarad are connected in series and the combination is charged to a potential difference of 120 volt. If the charge on the combination is 80 microfarad, the energy stored in the capacitor of capacity C in microjoule is how much? That is the concept. Look at this small circuit, whatever he has described there in the problem. I am just giving you in the form of a circuit here. There are two capacitors which are connected in series, he is talking. One this way, the second one this way. Both are now connected across a cell like this. What is the voltage of that cell given? 120 volt he has mentioned. This is 1 microfarad he said. This is C microfarad he said. That is one firstly. Now come to the second one please. He said that the charge in the combination on the combination is 8 microcoulomb. That is the point. Charge is going to be 80 microcoulomb. That is the one. Charge 80 microcoulomb means common sense says when both are connected in series, charge on the first condenser as well as charge on the second condenser, both should be equal to the same. That means in series combination, charge is the only quantity which remains constant. So what will be the charge on the first condenser now? C1 is going to be 1 microfarad and the value of charge on that one is 80 microcoulomb. Then what will be the PD across that one, please? V is equal to Q by C. Q is equal to CV formula. So 80 by 1, what will be that value? 80 volt is the PD across the first condenser. So 80 volt is the PD across the first condenser means out of 120, 80 is here. Then what will be the remaining? 40 volt automatically will be the remaining potential difference. Now look to the next case over here, please. What is the effective capacity? Effective capacity in series is C1 C2 by C1 plus C2, C by C plus 1. You can understand what is the total PD applied across 120 volt. What is the total charge across the system given? 80 microcoulomb. Of course, this also is microfarad. So take these three and relate them. Q is equal to CV, C by C plus 1 into 120. You can cut twice for 40, thrice 40. So 2C plus 2 is equal to 3C. Then C will be how much? 2 microfarad. So I am getting the value of C also. How much its value will now be? 2 microfarad as such. Now it is simple. What is the question is asking? What is the energy stored in the capacitor of C microfarad? Energy now is going to be half CV square C2 V2 square. C2 is how much? 2 microfarad into what is potential difference across that one? 40 whole square. It now becomes 1600. Cut this 2 off. These two zeros you can cut them off or directly you can cut this one minus 4 times. So what will be the energy here? 16 into 10 power minus 4 joule. But he has given, he is asking you the answer in microjoule. So no need for us to cut the things as well. So energy is now going to be 1600 microjoule. Directly you can write it like this only. So what is the correct option over here? Second option is going to be the correct option for this problem number 5. Look at the next number, that is problem 6. The plates in a parallel plate capacitor are separated by a distance d with air as a medium between the plates. In order to increase the capacity by 66%, a dielectric slab of dielectric constant 5 is introduced between the plates. What is the thickness of the dielectric slab? That is a question. 66% he is increasing or enhancing the capacity of the system. So you can certainly understand, before enhancing the system, capacity is going to be epsilon naught A by D. That is the concept. Now 66% it is increasing. That means what? 66% more means, won't it become for 166 more? So we can write 166 by 100 of this C must be equal to epsilon naught A by D minus T plus T by K. That is the formula. What is the thickness of the slab he is asking, and he is giving us the dielectric constant value as 5 over here. So what you can cut this one first of all? Epsilon naught A becomes cancelled. Fine. Now simplify this one. In what manner? 166, that means 83 times 2 and 50 times 2. Come on, cross multiply this one please. Right? 83 times D minus 83 times T plus 83 times T by 5 is equal to 50 times D. Now you can directly get this one over here. It now becomes 33D is equal to 83T minus 83T by 5. If I take LCM here 5 times 83 times T minus 83 times T, 4 times 83 times T. That is the concept. So what is the value of T, the question? So 5 times 33 by 4 times 83 into D value. If you carefully observe these two products, this goes nearly 2 times. Nearly 2 times means what will be this ultimate value please? D by 2 must now be the thickness of that dielectric slab which is introduced between the plates of this condenser. That means the option must be the second option for this one, which is to be D by 2 as such. That is for problem number 6. Look at the next problem, that is problem number 7 please. A parallel plate capacitor with air as dielectric is charged to a potential V using a battery. Removing the battery, the charged capacitor is then connected across an identical uncharged parallel plate capacitor filled with wax of dielectric constant of K. The common potential of both the capacitors is how much? That is the concept. Common potential, that is the concept actually. V common if you take up. Already I have told you uncharged means that will not have any charge. That will not even have potential difference also. So C1 V1 plus C2 V2 by C1 plus C2 is the concept actually. C1 V1 that is CV plus C2 V2 that is 0 because that is uncharged by C1 plus C2. What is C1 now? K times C. Why K times? Now dielectric of constant K is introduced between the plates of the condenser. So automatically the capacity becomes K times plus C. That means what we can write, see if you take common, V by K plus 1 is left over now. Look at that option number 4, V by K plus 1 volt. That is going to be the corresponding common potential of this particular concept please. Look at the next problem, problem number 8. A 4 microfarad capacitor is charged by 200 volt battery. It is then disconnected from the supply and is connected to another uncharged 2 microfarad capacitor. During the process, the loss of energy in joule is how much? That is the concept. Look at what exactly he is giving us the data. A 4 microfarad capacitor, 4 microfarad. And of course, what is the potential across that one he has given? V is going to be 200 volt. That is what has been provided to us. It is then disconnected from the supply and is connected to another uncharged 2 microfarad capacitor. That means C2 this time is going to be 2 microfarad capacitor. Once again, V will be same 200 volt only. He is not changing that value anymore. What is going to be the loss of energy is the concept. You can first of all take loss of energy. Loss of energy in this particular case, he is talking about the second one is uncharged. Uncharged means second one initially is not going to have any voltage. After connecting only 200 will be taken up there. So loss in energy, what is the formula now to be taken up? Half of C1 C2 by C1 plus C2 into V1 minus V2 whole square. That is the formula one should take up. So if you just substitute the values of C1, C2, V2 is going to be how much now? 0. What for you people can better understand? Second one is uncharged he is talking. Then automatically V2 will be 0. So if you apply this formula directly and substitute the values over there and simplify, you will be getting 8 by 3 into 10 power minus 2. 8 by 3 into 10 power minus 2. That in the sense what? You will be getting 2.67 into 10 power minus 2 joule. That is going to be the loss of energy there. So what you should understand in this case is fourth option is the correct option for this question number 8 please. Look at the next number, that is problem number 9. Energy is stored in a parallel plate capacitor C1. An identical uncharged capacitor C2 is connected to it, kept in contact with it for a while and then disconnected. The energy stored in C2 is going to be how much? That is the concept once again. Almost the same concept even here also. The concept here is the very first capacitor is given C1. And of course, uncharged, its energy is going to be half C1 V square. That is the formula generally. Now, this is even if I write, that is the value given in the problem as E. Second one is C2, that is uncharged he said. Then what will be the common potential that can be calculated please? C1 V1 plus C2V2 by C1 plus C2. That of course C1 plus C2 I can write same because they are identical. That is a point. So what can we write now in this case? V by 2 you will be getting. Now automatically what will be the energy? Half C into V by 2 whole square. V by 2 whole square, is it not 1/4 of half CV square, please? What is half CV square? Already has given you as E. Then what will be your answer ultimately? It should now be 1/4 of the total value. That means the option must be the third option over here. That is the concept what you need to understand. So how to calculate common potential, I think all of you are following. Come to the next one, that is problem number 10. If you look at the plates of a parallel plate capacitor are charged up to 200 volt. A dielectric slab of thickness 4 mm is inserted between the plates. Then to maintain the same potential difference between the plates of a capacitor, the distance between the plates is increased by 3.2 mm. The dielectric constant of dielectric slab is how much? That is the concept. Look at first of all, before just introducing the dielectric, epsilon naught A by D, the general formula for capacity. To maintain the same capacity, what do you mean by that? Even after introducing the dielectric also, its capacity should be similar to this value. Then what is the formula we have to adopt? Epsilon naught A by D minus T plus T by K formula. But what he said, to maintain the same old capacity, distance between the plates is increased by 3.2 mm. So D plus 3.2 minus T, right? D minus T plus T by K, these two are to be equated. So if you cancel these two off in the numerator, D also gets cancelled over here. So what is now left over? You check this one. D is equal to D plus 3.2 minus, what is the thickness given? 4 plus 4 by K. Now D getting cancelled, what will be left? 4 by K will be 4 minus 3.2, which now becomes 0.8. Then what will be the value of K? 4 by 0.8. 0.8 goes in 4 exactly 5 times. So what will be the dielectric constant of the medium there? It should be 5. So third option is going to be correct option for this problem number 10. Look at the next number, that is problem 11. A parallel plate capacitor filled with a material of dielectric constant K is charged to a certain voltage. When the dielectric material is removed, then what happens? Identify very easily, you can identify this one. When dielectric is removed, automatically capacity decreases K times. That means what? The capacitance decreases by a factor K. So A is supposed to be correct. Electric field strength reduces by a factor K. In fact, electric field strength does not reduce, it increases. So second B is wrong. The voltage across a capacitor increases by a factor K. That is exactly correct once again. The charge stored in the capacitor increases. Charge in fact will not be increased over here. So A and C are supposed to be correct. That means the second option is going to be true. This also is one of the EAMCET questions only. Look at the next problem, that is problem number 12. The capacitance of a capacitor becomes 7 by 6 times its original value if a dielectric slab of thickness T is equal to 2D by 3 is introduced between the plates. If D is the separation between the plates, the dielectric constant of the dielectric slab is how much? Capacitance of a capacitor becomes 7 by 6 times the original value. That is the point. So you can write 7 by 6 times epsilon naught A by D must now be equal to epsilon naught A by D minus T plus T by K. D is the distance minus what is the thickness given? 2D by 3 plus 2D by 3 into what is the dielectric constant he is asking us to calculate. Therefore, I write that one as K only. Now epsilon naught A gets cancelled over here. Then what is now left over? You just check. First of all, 7 by 6D is equal to 1 by, I take D common here, 1 minus 2 by 3 plus 2 by 3K. I can write like this. D once again gets cancelled. Come on, cross multiply this one. 6 is equal to 7 minus 14 by 3 plus 14 by 3k. So you can write 14 by 3k now will be how much? You just take these things, that's the other side. 6 minus 7 plus 14 by 3. Now whatever the value of k, that is the question over here. K now becomes 14 by 11. That k value will be 14 by 11 you will get. That is going to be the very first option for us. That is the concept what you have to take up here. That means it is the value 14 by 11. That is the question. So first option is going to be true for this question, please. Look at the next one, that is problem number 13. A parallel plate capacitor of capacity C0 is charged to a potential V0. The energy stored in the capacitor when the battery is disconnected and the plate separation is doubled is E1. Observe carefully, battery is disconnected means we should understand charge remains constant. Then what will be E1 now? Half Q square by C. But you can understand well, as in when the distance of separation between the plates is doubled, C becomes half. So you can write 2Q square by 2C. That means C 2 gets cancelled. Q square by C, that is our first value of E1. What is B he has given you, you see there. The energy is stored in the capacitor when the charging battery is kept connected and then the separation between the capacitor plates is doubled. Then what happens? E1 is equal to half C by 2 into V square this time. So how much it will now be? CV square by 4. That is the one. Now what is this question there? What is E1 by E2? If I take E1 by E2. Now it is Q square by C. What is Q square? C square V square by C into 4 by CV square. Now V square gets cancelled. This C into C square gets cancelled. What is now left over? 4. So your answer must be simply 4:1 like. That means the first option which is given as 4, that is the correct option for us. That is the point. Now come to the next one, that is problem number 14. Between the plates of a parallel plate capacitor of capacity C, two parallel plates of the same material and area, same as the plate of the original capacitor, are placed. If the thickness of the two plates each is equal to 1/5 of the distance between the plates of the original capacitor, then the capacity of the new capacitor will be how much? That is the concept. In fact, we can understand the capacity is equal to epsilon naught A by D, that is the original value. Now what is the capacity is the question. Epsilon naught A by D minus T plus T by K we people can write. But one thing you should understand, what is it he is giving? Same material he is introducing. Material means definitely that will be a metal. So T by K will be 0. Then what will be the value? Epsilon naught A by D minus T. What is the value of each thickness? 1/5 times D. Like that how many? 2 plates. So 2D by 5 I can write. Then what happens to this one? Epsilon naught A by 5D minus 2D, 3D by 5. So is it not 5 by 3 times epsilon naught A by D, please? What is epsilon naught A by D? It is original capacity. So we can now write 5C by 3 must now be the present capacity of the system. That means option must be the first option over here in this problem number 14. Look at the next one, that is problem number 15. A parallel plate capacitor of capacity 100 microfarad is charged by a battery of 50 volt. The battery remains connected, and if the plates of the capacitor are separated so that the distance between them becomes double the original distance, the additional energy given by the battery to the capacitor, recollect that, additional energy given by the battery. By the battery means what is the concept there? Original energy. Energy is nothing other than QV. So what we should understand, additional energy in this particular case is Q1 minus Q2 into V. That is the formula what you have to take up. So what is Q1 over here? Q1 is equal to CV. What is C given? 100 microfarad into the value of V. What is that V given? 50 he has given. So 100 into 50 microcoulomb I can take. What is the next one? That is Q2. The moment the distance of separation is increased to double between the plates, automatically capacity becomes half. So it now becomes 50 into 50 microcoulomb here. And what is the PD over here given? 50 volt. Just substitute these three values here and simplify. You will be getting exactly 125 into 10 to the power minus 3. 125 into 10 power minus 3 joule. That is going to be the corresponding energy. So this is going to be the case. You should understand E is equal to QV, the formula. Q1 minus Q2 into V. That is the additional charge provided by the battery as such. Look at the next one, problem 16. The time in seconds required to produce a potential difference of 20 volt across a capacitor of 1000 microfarad when it is charged at the steady rate of 200 microcoulomb per second is how much? That is the concept. Look at this 16th question please. First of all, he has given you two values. 20 volt is going to be the potential difference PD. Fine. What next he has given? 1000 microfarad is going to be the capacity given. Taking these two, can't you just calculate what is the charge please? Q is equal to CV. 1000 into 10 power minus 6 into 20. 1 0, 2, 3, 4 zeros. I can cut minus 2 times. So 2 into 10 power minus 2 coulomb. That is the charge. But be careful with the last number given. 200 microcoulomb per second. Come on, separate that one. 200 microcoulomb charge in 1 second we people are getting. Then 2 into 10 power minus 2 coulomb in how much time it takes for us to get this much of charge. So you can write 2 into 10 power minus 2 divided by 200 into 10 power minus 6. You can cut these two zeros minus 4 times. 2 getting cancelled. You are now left with 100. What? 100 seconds time it takes to get this much of charge on that. So correct option for this question number 16 is to be the second one here. Look at that next number, that is 17. The capacities of the capacitors are in the ratio 1:2:3. Their equivalent capacity when connected in parallel is 60/11 microfarad. More than that when they are connected in series. Their individual capacities in microfarad are how much? That is the concept. Look at the next case please. C1 you take it as C. C2 you take it as 2C. C3 you take it as 3C. Why? Because 1:2:3 he gave. Now when connected in parallel, C parallel is equal to C series plus 60/11. That is what he is talking about. So what is C parallel in this case? C plus 2C plus 3C. 6C is equal to. What is C series please? 1 by C series is equal to 1 by C plus 1 by 2C plus 1 by 3C. Then what will be the LCM over here? 6C I can write. 6 plus 3 plus 2. 11 by 6C. Then what will be the C value of series please? C series now will be 6C by 11. Write that one over here. 6C by 11 plus 60 by 11. Now you can certainly write this one 60 plus 6C by 11. Come on, cross multiply this one please. 60 plus 6C is equal to 66C. 6 into 11. Now this goes there. C becomes 1. Then what will be C1 then? C1 must be 1 microfarad. What should be C2 then? 2 microfarad. What should be C3 then? 3 microfarad. What are the three capacitors this fellow is asking? 1, 2 and 3 microfarad are supposed to be the values for this. The option is going to be the second one for this particular question. Look at the next one, that is problem number 18. A capacitor of capacity 10 microfarad is charged to 40 volt and a second capacitor of capacity 15 microfarad is charged to 30 volt. If they are connected in parallel, the amount of charge that flows from the smaller capacitor to higher capacitor in microcoulomb is how much? That is the concept he is asking. Look at carefully now. First one you can take, C1 is given 10 microfarad. What is the corresponding voltage he has mentioned? 40 volt he said. Fine. What is C2 he said? It is 15 microfarad. And how much is the potential across that one he said? That is given as 30 volt he said. So first you take the first one and write what is the charge on it. Q1 is equal to C1 V1. Directly you will be getting 400 microcoulomb. Now what will be the common potential when these two are connected? It is C1 V1 plus C2 V2 by C1 plus C2, that is 25. 400 here and of course 450 here, 850 by 25. Directly you can say 3 times 75 and of course 100 means 4 times. So 34 volt is the PD. Now you can certainly understand what will be the charge on the first capacitor now. Q1 dash is C1 into common potential. What is C1? 10. What is common potential? 34. What will be the total value? 340 microcoulomb. Look at earlier value now. 400 microcoulomb. What is the present value now? 340 microcoulomb. So how much it is losing? 60 microcoulomb is going to be the capacity. That is of course flowing from one to the other. So option must be the second one for this particular problem number 18. Look at the next one, that is problem 19 please. A body of capacity 4 microfarad is charged to 80 volt and another body of capacity 6 microfarad is charged to 30 volt. When they are connected, the energy lost by 4 microfarad capacitor is how much? Energy lost, once again you people have to understand straight away. Loss of energy has got a direct formula for us, that is half of C1 C2 by C1 plus C2 into V1 minus V2 whole square. What are the values given? You see there. C1 is 4, C2 is given 6, V1 is given 80, V2 is given 30. Substitute the values over there. The loss of course you will be getting exactly 7.8 millijoule for this particular question as such. So remember this loss of energy formula directly. This is for the question number 19. Look at the next one, problem number 20 please. A 20 farad capacitor is charged to 5 volt and isolated. It is then connected in parallel with an uncharged 30 farad capacitor. The decrease in energy of the system, once again energy he is talking about. So firstly what you should understand please, what is the energy in the first case? Directly you can write potential is given, so half CV square. You can directly write half into C being 20 into V square is going to be 25. Directly you will be getting 250 what? Directly joule you can write. Fine. Now the next concept is what will be the common potential at present? What will be common potential please? C1 V1 by C1 plus C2. That is now going to be 20 plus 30. It's going to be 50. This goes 10 times and you are left with 2 volt now. Now what is going to be the decrease in energy? What will be E2? You directly take up now. C is going to be 20. 2 square means 4. 2 into that of course you can directly write the energy in this particular case you can take up half of the effective value of C into V square. That is common square you take up. Now after getting these two, whatever is the difference, you will be getting this value to be exactly 100 joule. So what will be the difference over here? 150 joule must be the loss or decrease in energy. That's what one has to take up over here, please. So look at this area carefully. Directly 150 joule is going to be the decreasement in the capacitor, in the energy of the condenser as such. Look at the next one, that is problem number 21. A parallel plate capacitor of capacity 5 microfarad and plate separation 6 centimeter is connected to 1 volt battery and is charged. A dielectric of dielectric constant 4 and thickness 4 centimeter is introduced into the capacitor. The additional charge that flows into the capacitor from the battery is going to be how much? Once again the same model almost, numbers are given different and in a slightly different manner he is asking. The capacity value he has given you 5 microfarad, that can be written as epsilon naught A by D. No change in that whatsoever. And what is the capacity now, please? Epsilon naught A by D minus T plus T by K. Now epsilon naught A, you take it as it is, please. What is the distance of separation? 6 centimeter. What is the thickness he has mentioned there? 4 centimeter. Plus 4 by, what is the value of dielectric constant given again? That also is given 4. So what will you get here? Epsilon naught A by, this gets 1, 6 plus 1, 7 minus 4, it now becomes 3. But what is this value? Epsilon naught A by D, D is given how much there? 6 centimeter, so that much is going to be 5. Then what will be the value of epsilon naught A, please? It is 6 times 5. That value you take it over here. So 6 times 5 by 3. This goes twice. So what will you get now? 10 you will get. So 10 microfarad. That of course is going to be the value. But what is this question you see? Additional charge. Earlier it was 15. Now it is 10. Then what? Earlier it was 5. Now it is 10. What will be the additional charge here? It is now going to be 10 minus 5, which now becomes 5 microfarad as such. So what is the correct option there, please? Third option is going to be correct for us. Let us check the last number in this order, please. A parallel plate capacitor filled with a dielectric of relative permittivity 5 between its plates is charged to acquire an energy E and isolated. If the dielectric is replaced by another of relative permittivity 2, its energy becomes how much? That is the concept. Look at now carefully, what is the formula for energy? Energy is equal to half CV square. Firstly, he is just introducing a dielectric of constant 5. Permittivity 5, relative permittivity 5 means what? This now to be taken half of 5C into V square. That is the first equation for E1 I can write. What next he is talking? This time he has replaced that relative permittivity 5 material. He has introduced a material of relative permittivity 2 this time. Then how to write that? Half of 2C into V square. That is going to be the second one. Now the question here is, what is the ratio of E1 by E2? You take that. Half into CV square whole multiplied by 5 this one by half into CV square whole multiplied by 2. This whole thing gets cancelled. So what is now left over? 2.5 is left over, 5 by 2. Then what will be the value of E1? Is it not 2.5 times E2, please? E1 is 5 times, E2 is 2 times. So 5 by 2 is 2.5 times. So directly you can write E1 is equal to 2.5 times E2. That of course you can say, if one value is given as E directly, you can take that one as 2.5 times E. So this is actually the one what we have to consider over here. So the way in which the capacity that varies, that is the one which we people have to take up. Now the same, suppose if I take voltage constant. Suppose the same question if I take energy in terms of charge, please. Q square by C. If I take that one, same concept I will get E2 is equal to 2.5 times E1. So whichever one that fellow is asking, according to that we can mold the formula there. So these are the different questions which we have taken from the past 10 years of EAMCET papers today. So all these models, whatever they have given in previous EAMCET papers, if you just work them out perfectly, I am sure that every one of you can secure 1 to 2 marks. If they give both the questions from capacitors, both the questions, of course 2 marks you can secure from this particular slot. So this is about electrostatics, whatever we have. In the next session, we are going to switch over to the concept of current electricity and applications thereby.